Good evening. You're welcome to this class. I must apologize. I'm sorry for the class we scheduled to take place on Thursday. It could not hold due to network problems. When the class started, I had some network failure, so we could not be able to continue with the class. So it was rescheduled for today. So today is our fourth lecture in CHM 307. Atomic molecular structure and symmetry. Today in this class, we'll be looking at molecular orbital, the description of homonuclear diatomic molecules using the molecular orbital theory. We'll try again to define the bond order and look at the important consequences of the molecular orbital theory. If time permits, we'll look at the molecular orbital theory description of the heteronuclear diatomic molecule and also take a particular example of hydrogen fluoride. And if time permits, we'll look at the Hooker's theory. The molecular orbital, as we discussed previously, is a construction by combining atomic orbitals or hybrid orbitals from each atom of a molecule, which actually come together to form what you actually call the molecular orbital. The molecular orbital is represented by the linear combination of molecular orbital molecular orbital method. So generally in most books you will see it as LCMO-MO methods. Most methods in computational chemistry today starts by calculating molecular orbitals of the atom. So the knowledge of the molecular orbitals is very, very important in the study of chemistry, particularly in computational chemistry, which is one of the reigning branches of chemistry that we have nowadays. A molecular orbital describes the behavior of an electron in the electrostatic field generated by the nuclei. So once an electron finds itself in an electrostatic field, there is a field that is generated along the nuclei. A field is generated. So the probability of finding this very particular electron, as we discussed, is it in our second or third lecture, is found within the localization of the atomic orbitals combining together with each other. In the case of two electrons occupying the same orbit, the polar exclusion principles actually applies. That means no two electrons occupying an orbital can have the same spin. They must always have opposite spin. So you apply the polar exclusion principle in filling in of electrons into the molecular orbitals of atoms. Molecular orbital in general can be defined as a mathematical function that describes the wave-like behavior of an electron in a molecule, the wave-like behavior of an electron in a molecule. Hence, this function is used to calculate both chemical and physical properties, such as probability of finding an electron in any specific region of the electromagnetic field. The molecular orbital theory for homonuclear diatomic molecules states that only the atomic orbitals having similar energy will combine to form a molecular orbital. I take that again. Only the atomic orbitals that have similar energy that can combine to form a molecular orbital. So that means that atomic orbitals that have different energy, particularly if the gap is very, very high between the two, they cannot be able to combine to form molecular orbitals. It's only those that have similar energy. An example, if you have a paper, you can take note. An example is if you have a 1s plus a 1s orbital, or 2s plus 2s orbital. When 1s and 1s come together, they have similar energy, they can combine. When 2s and 2s of the same atom come together, they have similar energy, they can combine. In other words, you can say the orbital of 1s can combine 1sa, that is the atomic orbital of the electrons of atom A plus the atomic orbital of the electrons of atom B. So 1s can give you 1sa plus 1sb. Or you can have sigma s, which is equals to 1sa minus 1sb. Or you have 2s, which will give you 2sa plus 2sb, or 2s star, which is equals to 2sa minus 2sb. Where it is a minus, thus there is always a subtraction. Like we said before, that bonding molecular orbital adds to bond formation, while antibonding molecular orbital adds to bond breakage. So once electrons go into the bonding molecular orbital, they are adding to bond formation. And once electrons are going into the antibonding molecular orbital, they are adding to bond breakage. And each of the orbital that you see that is asterisk, the one that is asterisk is antibonding. And the one which is not asterisk is not antibonding. Let's take a look at the slide we have here. That is in slide 3 that we have. The molecular orbital of molecule 1 will be equal to the atomic orbital of atom A plus the atomic orbital of atom B. And the molecular orbital of molecule 1 can also be equal to the atomic orbital of atom A minus atomic orbital of atom B. And like we said earlier, the molecular orbitals must have many molecular orbitals as they are atomic orbitals, and they try to combine together. If you look at the next slide that we have, that is slide 4, you will see the figures there. One s atomic orbital plus another s atomic orbital. That is a wave function of a combined sigma 1s, combined sigma 1s. So an example is if you have two hydrogen atoms you are bringing together, they give you something intermediate like what you are seeing in between the A and B. It's like an egg, two eggs brought together. Now in B, you see the bonding probability. That is, the two have been mixed together. It forms something that looks spherical like an egg. So the probability of finding an electron is found within that very particular region. Now, if you look at the second, which is the anti-bonding, or sigma 1s star, we can call it. You have 1s from atom A, another 1s from atom B with a different spin. The two of them are actually with different energy, two of them are coming together. So their mixture is what you see at the intermediate state. The peak of one is opposite to the peak of the other. So it is actually destructive. It doesn't lead to combination because it is anti-bonding. It is destructive. It does not lead to combination. Hence, the resultant product is the anti-bonding probability density you see in D. That is the two atoms, even though because of effect of electric field, there is tendency for the two to be pulled to come together, but they are not coming together. Hence, a bond is not formed between the two of them at all. If we try to go forward or pick maybe the molecular orbital diagram, like we discussed in our previous class. So you have a construction of the molecular orbital diagram. You have on both sides, left and right, the atomic orbitals, which are intermediate in energy. The bonding molecular orbital is lower in energy than the atomic molecular orbitals. That is the one you see below. Now, the antibonding molecular orbitals, which are higher in energy than the atomic orbitals, they are the ones that are found above. The molecular orbitals are sigma 1s. The antibonding molecular orbital are sigma star 1s. Now, if these the two are hydrogen atoms with one electron, so one electron will come from the hydrogen atom on the left-hand side, and another electron will be donated from the hydrogen atom on the right-hand side. Take note, Pauler's exclusion principle is strictly adhered to here. The two electrons must have opposite spin, and that is what you are seeing in the diagram before you in the bonding molecular orbital in sigma 1s. That is, the two electrons are there. Now, considering the fact that hydrogen has only one electron, and the two electrons have gone into the lower energy molecular orbital sigma 1s, there is no available electron again that can go to the antibonding sigma 1s molecular orbital. Hence, there are no electrons at the antibonding molecular orbital, but there are two electrons at the bonding molecular orbital. Now, that brings us to the definition of bond order. Bond order is the number of electrons in the bonding molecular orbital minus the number of electrons in the antibonding molecular orbital, divide it by 2. So in the case of a hydrogen molecule that we can see, we have 2 electrons in the bonding molecular orbital, while there is no electron in the antibonding molecular orbital. Hence, the bond order is 2 minus 0 divided by 2. That is 2 over 2. And 2 divided by 2 is equal to 1. That's the proof why hydrogen can exist as a diatomic molecule with one single bond between the two hydrogen atoms. In some books, you may see the bond order being defined as the number of paired electrons in the bonding molecular orbital minus the number of paired electrons in the anti-bonding molecular orbital. So if we also try to apply that to what we have in the diagram before us, in the bonding molecular orbital, there is one paired electron. In the anti-bonding molecular orbital, there is no electron at all. So your bond order here will be 1 minus 0, which is equal to 1. And that is still a proof why there is one hydrogen bond that exists between a hydrogen molecule, or otherwise you can say that's why hydrogen actually is diatomic, because there are two bonds that are existing. There is a single bond that binds the two hydrogen atoms together. Bond order is useful in the sense that it's a useful quantity for describing the characteristics of bonds, because it correlates with bond length and bond strength. If bond order between atoms of a given pair of electrons is higher, then the bond length will be shorter, and consequently, the bond will be stronger. Take note of that again. I said the bond order is an important quantity for describing the characteristic of bond, and it correlates with bond length and bond strength. If bond order between atoms of a given pair of electrons is higher, then the bond length will be stronger and the corresponding bond will be stronger. If the bond strength is measured by bond dissociation energy, which is the energy required to separate atoms to infinity. That is the energy you can be able to apply to break a bond, to set the two atoms free. And that is the bond energy. And the bond energy actually is determined by the bond strength. The stronger the bond, the more the energy that is required to be able to separate the two atoms together away. The less stronger the bond, less the energy that is required to be applied so that the two atoms can be kept separate from each other. So in the case, the bond order, you can have bond order of 1 for a single bond order of 2 for a double bond, and a bond order of 3 for a triple bond. So, and you can also have a bond order of 0. Bond order of 0 is an indication that there's no bond that exists between the two atoms. That's why the bond order is 0. It means that if there is no bond that is existing between them. A typical example is helium. Helium has 2 electrons. So if we still look at the typical example of the molecular orbital diagram that we have earlier, helium atoms on both sides with two electrons. So each atom is going to donate one electron to the bonding molecular orbital, that will be 2. And the next 2 electrons will go to the anti-bonding molecular orbital, that is also 2. Going by our definition of bond order, if we use the first generation definition, that is the number of electrons in the bonding molecular orbital minus the number of electrons in the anti-bonding molecular orbital divided by 2. So that will give you 2 minus 2, which is 0, divided by 2 is 0. So no bond exists. Or if you look at the second definition, number of paired electrons in the bonding molecular orbitals minus the number of paired electrons in the anti-bonding molecular orbitals. That will result to, that is going to result to having 2, 1 minus 1, and 1 minus 1 is 0. And that's why helium does not exist as a diatomic molecule. However, helium ion can exist. Helium ion can exist. And helium ion exists simply because there will be half an electron that will be left at the end of the day. So, and that's why you can have helium ion. Now, the next objective we have is the important consequences or the importance that we can derive from this theory, that is the molecular orbital theory. One is that it predicts whether molecules can exist or they cannot exist. And it gives you an explanation on why such a molecule can exist in one form or not. Typical example is the helium we talked about. This, the molecular orbital theory, help you in explaining the fact that helium cannot exist as a diatomic molecule. However, helium ion can, because of at the bond order will give you half, so it can exist. The second importance of the molecular orbital theory that we derive from what we have said so far is that it's able to explain the paramagnetic properties of some molecule like oxygen, which we have not been able to actually look at them. But if we draw the molecular orbital diagram of oxygen atom having uh, 8 electrons each on both sides. If you try to construct the molecular orbital diagram, at the end of the day, you will discover that there will be a parallel electron that will be left on the diagram at the end of the day. And that explains why oxygen exhibit paramagnetic behavior. You can take your time, look at Concise Inorganic Chemistry. It's a book that also tries to give a detailed explanation on this very particular paramagnetic behavior of oxygen. And that's another thing that the molecular orbital theory has been able to help us explain in the field of chemistry. The next thing we will try to look at is the molecular orbital theory of heteronuclear diatomic molecules, So in order to develop the molecular orbital description of heteronuclear diatomic molecules, we need to consider the fact that the different types of atoms have different capacities to attract electrons. And the fact that the two different atoms are also very, very different from one another. And only atoms that have electronegativity that is almost similar to one another that can be able to combine together. So basically, the electronegativity of the bonded atoms plays vital role in the treatment of heteronuclear bond. The bonding electron will be much more stable in the presence of the nucleus of an atom that is having a greater electronegativity. That is the atom having lower energy. It is more stable, and therefore forming a bond with that atom can make that molecule become much more stable. The probability of finding the bonded electrons will be more near the nucleus. So the electron cloud will be distorted towards the nucleus, and hence the molecular orbital will resemble that of atomic orbital more than the atomic orbital on the electronegative atom. This description can easily describe the polarity of the heteronuclear diatomic molecules. A typical example of this which we can look at is the hydrogen fluoride. So let's, on our own as an assignment, try to look at the molecular orbital diagram of hydrogen fluoride, which is a electronuclear diatomic molecule, and how it is actually constructed. Now, the bonding in polyatomic molecules was actually explained by the Hooke theory. The Hooke theory said that polyatomic molecules, their combination among the atomic orbitals is complicated. Hence, one widely used approximate theory or a particular theory in trying to give an explanation to the formation of bond actually in polyatomic molecules. It also tried to explain based on the treatment of pi electrons, because there is pi electron bonding that exists in polyatomic molecules. So the Hooke theory tried to give a vivid explanation of what is actually happening there. So it illustrated as the number of atoms in the two atoms. So the nuclear orbitals are of the same form. And when they donate electrons to one another, some of them overlaps at different level. And so they were forming the pi bond. And that is actually sometimes the reason why also the pi bond are not as strong as the sigma bond. And that's why the pi bonds are also softer as compared to the sigma bond. Now, in summary, we can say that the molecular orbitals are usually obtained from combination of atomic orbitals, or what you call the hybrid orbitals. And the molecular orbital is a mathematical function that describes the wave-like behavior of an electron in the molecule. We can also say that the net bonding in a diatomic molecule is defined by the quantity called the bond order, is defined by the quantity that is called the bond order. Once more, I want to take this opportunity to also thank you all for your ability to participate in this very particular class that we have today. So we'll see in the next class. Thank you very much.